Welcome, everyone. My name is Josh Nguyen, and I am a student at the University of Pennsylvania and the Australian National University. I represent University BD, a group of over 40 researchers, students, and industry partners aiming to explore and examine the prospects of large language models and generative models at large in astronomical research. In this talk, I will present our work titled AstroLLaMA towards specialized foundation models in astronomy. Large language models perhaps need no introduction. Models such as Google's BERT, Microsoft's Palm, and OpenAI's ChatGPT have made remarkable leaps in all aspects of daily life. Trained on massive amounts of data, these models demonstrate impressive generalization performance by creating extremely human-like texts. So we ask ourselves this question: what does it mean for astronomy? Many applications come to mind. LLMs can help us summarize research articles, find relevant papers through information retrieval systems, generate interesting hypotheses based on the existing literature, and many more. Here is an example my colleague Joe and Yuan-San presented recently when they played with GPT-4. The model seems to do a very good job of summarizing one of Joe's papers with remarkable accuracy. Given the large and pervasive nature of astronomical research, this result seems to suggest it is promising to use LLMs to assist us with navigating this vast literature. LLMs are not without limitations. It doesn't take you long to find out that while ChatGPT seems very versed in answering a range of generic questions, when it comes to specialized domains, it is especially lacking. In astronomy, this can be a serious lack of scientific accuracy, a phenomenon often called hallucination. Language models are trained to complete texts from a statistical point of view, but few of them are explicitly trained to respect certain facts that are essential to scientific publication. Hallucination can be attributed to the fact that LLMs are trained using a very large corpus of texts, and research papers only occupy a tiny portion of it. The most effective way to address this issue is through fine-tuning, which is to adjust a model's parameters using a specific data set to achieve better application-specific performance. The first work to explore LLMs in astronomy is by Griezes and colleagues in 2021, in which the authors proposed to fine-tune the popular BERT model on astronomy datasets. The resulting model is called AstroBERT. A lot has happened since then, especially including the availability of many larger, more capable and open models. And our work aims to build upon AstroBERT's foundation and offer a new model with much wider downstream applications. So let's talk a bit more about fine-tuning, the focus of this paper. LLMs are statistical models trained to recognize patterns in text. In particular, they are trained using an extraordinary amount of text taken from many sources to predict what is called the next token. Fine-tuning refers to the process of adapting a language model to some specific data set for a downstream task. This task can be classification, text clustering, regression, similarity calibration, and so on. Through this process, we benefit both from the pre-trained model's general performance, which was acquired from its massive pre-trained data, as well as its application-specific performance, which was refined using our specialized data. In astronomy, we are well positioned to achieve this thanks to many open data sets and the availability of capable language models released recently. In this paper, we describe two main ingredients in fine-tuning in order to achieve a good model. First, we start with a pre-trained model. We choose the Llama 2 large language model by Meta AI, which was released in July 2023. This model has 7 billion parameters and was pre-trained using 2 trillion tokens. Second, we need a high-quality specialized dataset. We choose the archive paper repository and extract all papers categorized under astrophysics, which resulted in 300,000 plus articles. We further extract the abstracts of these papers, leading to a final dataset containing about 95 million tokens. And finally, we use Llama 2 and fine-tune it based on this dataset to achieve a new model, which we call AstroLLaMA. In particular, AstroLLaMA is used to predict the next token of an astronomy abstract, a task called causal language modeling. Compared to the base model it was adapted from, AstroLLaMA achieves a 30% better perplexity score, a metric for generative models, which indicates substantial improvement. In the rest of this talk, I will provide two preliminary results of AstroLLaMA's capability as a language model tailored to this literature. First, we examine AstroLLaMA's ability to complete abstracts given a short prompt. Here is an abstract of a paper by Chandra and others. We prompt GPT-4, Llama 2, and AstroLLaMA with the first few sentences and task them with completing the rest of the abstract. GPT-4 is currently state-of-the-art in language modeling. However, we find that its completion is too generic and off-target, even though it sounds quite natural. Llama 2, the base model of AstroLLaMA, typically gives a short and often off-topic continuation. On the other hand, AstroLLaMA exhibits remarkable content awareness in its completions by showing a deep understanding of astronomical concepts. Second, we test AstroLLaMA's ability to embed texts in the astronomy literature in a meaningful and semantically consistent way. We begin by taking 10,000 random abstracts from our dataset and embed them using AstroLLaMA and GPT-3. This plot at the top shows the distribution of cosine similarity between every pair of abstracts, where the higher the similarity, the more semantically similar two abstracts are on the x-axis. GPT-3 judges most papers to be very similar to each other with cosine similarities above 0.7 most of the time. On the other hand, the similarity scores produced by AstroLLaMA are much more diverse, suggesting a more nuanced representation of their semantic content. When examining specific examples, we find that the similarity scores by AstroLLaMA are indeed meaningful. In the example in pink at the bottom, for example, GPT-3 judges these two papers very similar when they're actually not. We suspect that this similarity stems from the common word magnetized, which may be a heuristic encoded within GPT-3. AstroLLaMA, by contrast, successfully distinguishes these two papers, reporting that they're not similar. To conclude, in this project, we explore the utility of large language models in assisting researchers in the astronomy discipline. We developed AstroLLaMA based on Llama 2 and a new dataset called from arXiv containing 300,000 abstracts. We have made the model, its training scripts, and training data available on Hugging Face. We also made available a paid playground on Hugging Face, which enables you to experiment with the model without having to download it to your local computer. It is our hope that AstroLLaMA will be adopted widely by the astronomy community, and we welcome new developments based on this starting point. And lastly, I'd like to thank my co-authors for their contributions in this journey. There is a lot of potential of LLMs that we have yet discovered, but we are as excited as ever. Thank you.